Video, we'd like to look at some examples of computing curvature. The first line that I would like, or first trajectory that I'd like to compute the curvature for, is a straight line. And if we just take a vector of a straight line, we can write that as it's, of course, point of origin, x0, z, y0, and then it's a directional vector being acted upon by the value, value parameter t. I can also write that, of course, out of a more compact form by putting each of its vector components into its position in the vector itself. So we'll let t go with range without bound and then compute the tangent vector. So that when we do that, we can see that it is no surprise that it just comes down to the directional vector. That certainly makes sense. And we compute the magnitude of the velocity vector, in other words, the magnitude of r prime, and find out that that's our root, or suspected, or regular root of the sum of the squares. So then when we end up computing that tangent vector as the ratio of the change to its speed, a unit tangent vector, is that we have the numerator is all constants and the denominator is a constant. So that when we take that derivative, we'll find out that then dt, the change of the tangent vector with time, is 0. So if we look at what happens to kappa, of course, that we know that kappa of s is going to be 1 over the change, the speed rather, times that magnitude of that change, dt, with time. Okay, so we already know that this is 0, so that the value of kappa is 0 and the curvature is 0. Let's rewrite that over here, and that the curvature is 0. So that if we look then in a similar kind of analysis with talking about the curvature on a circle, is that we can write a circle vector or circle trajectory and with a constant value of r, the radius, and allow the value of the parameter to go between 0 and 2 pi with just a positive radius, just to specify that. So then when we start to compute our tangent vector, we end up with minus r sine t in the x component and r cosine t in the y component. And then when we compute our speed, we find out that that is then the square root of minus r sine t quantity squared plus r cosine t quantity squared. So of course sine squared to cosine squared is 1, and we end up with this being the root of r squared equals r. Okay? So that we can find out that the speed there is r, so that when we find our unit tangent vector by using that speed, that we'll find out that we have the ratio of the sine and cosine, r cosine t, all over that constant r that we just found as the speed. So that then when we just cancel out the common factors, we have minus sine t cosine t. And that is our unit tangent vector. Okay. So then if we take the change of the unit tangent vector with time, we end up with a minus cosine t and minus sine t as our vector. So now again, we know the kappa here that we want to get our value is that we take 1 over the speed and multiply that by the change of the tangent vector with time. Okay. And in this particular case, I'm going to get 1 over r. We decided that's what our speed is up here. And that multiply that by that derivative that we just computed, sine t. Okay. So that we end up, the magnitude of that rather, there. Okay. And then now we compute 1 over r times the root. Okay. So that once we get kind of our common factor here, sine t of squared, is that, of course, the value under the radical is 1, and so that equals 1 over r. So there's our curvature, and remember that r is the radius of the circle. So that every time we start to talk about circles and figure out what their size or difference is that we can say, okay, well, here's a small circle, so that I have quite a bit of curvature as I go around here. Whereas in a very large circle, then I'm not going to have quite as much curvature because each of the changes as I go around is shallower. So that's the value of the radius, that depending on whatever the constant is, or whether the radius is rather, that will have a constant rate of curvature.